and this guy can move its amount up to its yield point, and now this guy gets to piggyback off of this guy's range. And so remember, one of the biggest downsides of flexure systems or compliant mechanisms, they have a finite limited range before they break or yield. And if you under-constrain a degree of freedom, like think of this case, this guy gets twice the motion range of this, and this guy gets twice the rotational range of this. Right? It can rotate this guy's amount and this guy's amount. Every time you have a redundant degree of freedom, you get twice the range, and sometimes that's great. And if you nest it cleverly like this, you can get twice the range in the same footprint as if you didn't have this. You know, this isn't taking up any extra space, right? And so sometimes under constraint is great to get much larger range. I mean, it always gets much larger range. Okay. Well, and you can also cleverly stack these so they get rid of parasitic error. So in truth, this guy wouldn't translate in a perfect straight line. It would actually arc down. And then if I held this guy fixed as the ground, this guy would arc up. But now if you allow this to arc down at the same time this arcs up, and these are the same length and spread pretty much the same distance apart, right? Or you know, reasonably, you know, and you tune this all so that these arcing down parasitic error motions cancel these arcing up parasitic error motions. Even though this guy's arcing, this stage that you care about does a pure, beautiful translation with no parasitic error. Okay, so you have to design it right, though, to do that. But you can only do that kind of parasitic error canceling with under-constrained things. Okay, so under-constraint can be great for getting rid of parasitic error and getting huge ranges. But beware, you're going to have some vibration issues in both quasi-static and dynamic scenarios that maybe you can tolerate. Okay? Okay, so to make my point even clearer here, let's look at this example. Okay? So, all right, so first of all, you look at this, and I'm going to say, is this a parallel system? Well, my first question is this under constraint, right? Well, the first thing you would do is say, well, is this parallel? Because if it's parallel, it's not under constraint, okay? Well, let's look at this. Hopefully, you know by now this is not parallel, okay? First of all, there's 3 rigid bodies in it. That's one big giveaway, okay? Secondly, this is clearly a parallel module here. You got this one connected to this one by that. That's one nice parallel module. And then here's a nice parallel module. You got this one connected to this guy with these guys. So it's got 2 parallel modules stacked in series. They're different parallel modules, though, right? So, but anyway, that doesn't matter. It's a serial system, okay? Okay, so now you say it's a serial system, so that means it's possible for it to be under constrained. It could be under constrained. Okay. All right. So you know it could be under constrained. The question is it? Well, is there a redundant degree of freedom? Well, ask yourself, what is the motion of this? If you hold this guy fixed and just forget about this guy, what is the motion of this guy? Well, if you remember from instant centers, if you draw a blue line up there, where they intersect is where this guy will be able to rotate. So you got your 2 constraints constraining this guy. They intersect right up at that point. If I drew this blue line up there and this blue line up there, this guy would be able to rotate around that axis right up there. Be able to rock like that. Okay? Okay, so that's the degree of freedom of this guy. Well, now if we hold this guy fixed, how does this guy move, this triangle? Well, again, it's got these 2 things that intersect at the same point, so it also rotates at that same point. Okay? And so you can imagine that guy dipping around there, rotating around that point. Okay, so the question is, do they have a redundant degree of freedom? Yes, they have the same rotation, and of course, it's not just a rotation, but they're at the same location and going in the same direction. To be redundant degree of freedom, they have to not just be both a rotation, they have to be the same rotation, at the same point with the same direction, and that's the case here. Okay, so then the answer is yes, it's under constraint. And let's do our final check here. If I hold this final stage that we care about fixed with respect to the ground, can this guy move? Yes, it will still be able to rotate there because it's the instant center. I mean, that now is effectively acting like a ground, and it's got its instant centers there. And this is the ground, and it's got the same instant center, so it could rock. Okay, so this is under constraint. Okay, but now what if I change the system like this? What if I put that there? Okay, well, look at what I changed. I did this. Okay, now the question is this under constraint? Well, it's still obviously a serial system. You know, it's got, here's one parallel module, right? You know, these 2 things. And then here's a parallel module connecting those two things. So it's a serial system, so it can be under constraint. The question is it? Well, now the degree of freedom of this guy, if I hold this fixed, is where these two guys intersect, somewhere approximately like maybe there or something, right? I don't know. And so this guy would now rotate around that axis. It's a rotation. But then this guy, if I hold this fixed, this guy now rotates around that same axis. Okay, so, right? So it's not under constraint because this guy, even though it has a rotation, and this guy, even though they have a rotation, they both have a rotation. They're not redundant rotations because they're not at the same location. They are both rotations, and they're both pointing out of the page. So they're almost the same, but they're different. This one's at this location, and that one's at that location, at the top of the point. So because they're different, they're not under constraint. They're not redundant. This is a serial system that is not, let's see, yes, this is a serial system that is not under constraint because it does not have redundant degrees of freedom. Okay? And if I hold this stage fixed with respect to the ground, this guy will be like a truss. This guy will be locked up. There's no way this guy's moving anywhere. These constraints, if that's the new ground and this is a ground, one common ground, this guy is locked up. It's not going anywhere. And so if you're driving this with actuators and stuff, you are just controlling this. This one is just locked up. You won't have any dynamic issues. You're good. Okay? If this is all ideal. Okay, so great. So you can see how, first of all, you can see how parallel things cannot be under constraint. Only serial and hybrid things can be under constraint. You can see what conditions make them under constraint or not under constraint. And hopefully you can see that exact and over-constraint have nothing to do with this concept. They deal with redundant or independent or non-redundant constraints. This deals with redundant or non-redundant degrees of freedom. Okay? So a system can be both over-constrained and under-constrained. A system can be exactly constrained and under-constrained, or exactly constrained and not under-constrained. But you cannot both be under-constrained and not under-constrained, or exactly constrained and over-constrained. Okay? So hopefully you understand that. If you don't, you're going to go through this. These principles are super important. These three things, like I said, are possibly the most important thing I can teach you in this class, and we're going to hit it a lot in this course, okay? So you will understand and go through this many, many times. Okay, so let's look at a new kind of element, blade or flexure element here. We've really only been looking at wires, okay? So let's start by looking at what we're familiar with, a wire here. So here we have, you ask yourself, is this a parallel or serial system? Well, it's obviously parallel. It's just two rigid bodies, and they're connected directly to each other. Here's the stage you care about. Here's the ground with the hatch marks on it, okay? Without any constraints, this is 6 degrees of freedom. With constraints, which we show here, this wire, you kill this translation. Now it has 5 degrees of freedom. Very good. And this is an exactly constrained system. So it's a parallel system, and it's exactly constrained because its wire is doing the single independent job of killing that thing, that translation. Okay? Okay, so let's add another. Which one does that one kill? Well, it pretty clearly kills this rotation. So we've got 2 constraints killing the translation and the rotation. This is an exactly constrained system. It's still parallel, obviously. Okay, it's still just 2 rigid bodies. So it's a parallel system that's exactly constrained. 4 degrees of freedom. All right, let's add another one. Okay, an angled one from there to there. Our brains don't like non-orthogonal things, but they can exist, obviously. So which one does this one kill? Well, imagine none of these could stretch. Well, let's actually look at it from a bird's eye view. Let's look at it. So here's the ground, here's the stage, and this is what the constraints look like. They're all in the same plane. Here's the angled one. Okay. Well, of these degrees of freedom, which one does it kill? Well, you couldn't translate this one, right, without stretching or compressing this one, because this one is no longer perpendicular or orthogonal to the axis of this. Remember, wire flexures, they constrain things along their axis so that they only permit translations perpendicular or orthogonal to their axis. Without this angled guy, this motion was perpendicular to those two, but it's certainly not perpendicular to this anymore. So that if you translated this stage in that direction, it wouldn't stretch these 2 vertical ones, but it would sure stretch this one with some component. And it's not allowed to do that, and so that one dies. So the answer is even these ones, the translation coming out, it's still orthogonal to all three of these, still perpendicular, so it wouldn't stretch any of them. And by twisting these, or bending and twisting that, it doesn't stretch any of them. So those are obviously degrees of freedom that are maintained. And this one is obviously, the translation is obviously the one that one kills. And those three guys are still doing their unique job, right? We got 3 constraints killing 3 degrees of freedom, 2 translations and 1 rotation. So this is indeed exactly constrained. All right, so very good, and there's those things. Now let's add this one. It's on the same plane, it's over there. Which one does that one kill? Well, put me on pause and think about it, but if you're done doing that, you'd stare at it and say, well, that one doesn't kill anything. So that's one that if we add or subtract, it's redundant. It's, the system is now over-constrained because it doesn't change the degrees of freedom. We're just stiffening the system and not changing the degrees of freedom. So this is now an over-constrained system. Okay, and it's still parallel, obviously. It's still 2 rigid bodies connected directly together by these wires. Okay. All right. So let's add another one. Okay. Well, that's even more over-constrained. This guy doesn't do anything. This is redundant as well. It's just 2 times now over-constrained. Okay, now say we keep adding a bunch, and now say we fill it. Okay, so say you added infinite wires in this plane, so you just filled it, and now it's just this big solid mass. Okay, well this guy is a blade flexure. Okay, this is what's called a blade flexure. Some people call it a leaf spring flexure, but it's a blade flexure. It's just a flat sheet of paper, almost a flat plane. And it can connect 2 rigid things. And these are the correct degrees of freedom it has, which, let me show you an animation. Here's the first 3 mode shapes. They're associated with natural frequencies that are much lower than the other higher mode shape natural frequencies. Okay? All right. And so very good. So that's how it would move. But I think I just proved to you, though, that this element is, in and of itself, over-constrained. Right? So in my little case study, this example was exactly constrained at this point and had the exact same degrees of freedom as this. Okay? By the way, things that have the exact same degree of freedom are said to be kinematically equivalent. They're equivalent kinematics. They have the same kinematics, the same degrees of freedom. They both can twist, bend, and translate. Kinematically equivalent. Okay? But this one is more exactly constrained than that one. Right? Because this one actually had 3 wires. And and they exactly constrained it. Whereas this guy was filled with, so far as we're concerned, infinite wires in its plane that made a nice thing. And so this one's over-constrained. Okay. Now in textbooks, sometimes you'll see people model with constraints flexure blades by drawing 3 blue lines like this, and it's because they're mimicking. Those are the 3 independent ones within the blade, right? And of course, they don't have to be. It's just they need to be 3 independent ones. They don't have to be those 3 specific independent ones. But anyway, you'll see in textbooks people will model flexure blades like that. So yes, this you will have more problems from over-constraint if you use this than this. Here's one concept I need to teach you about just reality is that nothing is truly perfectly exactly constrained. Okay. Even wires, they'd have to be infinitely thin and infinitely long. And of course, if they were infinitely thin, they would be, they'd buckle very easily in compression, and they'd snap immediately in tension as well. But the closer they are to infinitely thin, almost the better they model these things, as long as you don't allow them to be in compression. That's why a string is such a great way to exactly constrain something. It's just a cable. As long as you don't put it in compression, acts more like an ideal constraint. Okay, but the truth is, once they have some finite thickness, you can fit more blue lines in their geometry and connect these 2 rigid bodies, and they can be kind of off angle. They don't have to be in the axis perfectly, and it starts constraining unwanted directions that over-constrain things a bit. So the truth is, over an exact constraint, even though in theory it's like black and white, it's like you're either exactly constrained or you're either over-constrained, in reality, when you add all the gray, and your ideal constraints aren't infinitely stiff and infinitely compliant in different directions. With all these assumptions, you actually allow reality to add its grayness to it. You actually never perfectly exactly constrained. You're just closer to exactly constrained than over-constrained. And in this case, this scenario would be closer to exact constraint than this. This is more over-constrained. But because the blade is made of a single piece, I mean, no one would assemble infinite wires to make this blade, obviously. You'd cut this out of a piece of metal, or you would, it would just be a shim that you'd get and you could assemble it in your system or something. But there's nothing assembled within the blade, and so the issues of over-constraint aren't that bad of just using a blade by itself, and it's just not useful to consider it to be over-constrained when you're using it. And that's true of any element, whether it's a wire or a blade or a notch flexure or anything. No element is of itself over-constraining itself. Instead, it's more useful to use this concept of order of constraint. So by itself, this is not considered over-constraint in practice. It has an order of constraint of 3, though, because it has 3 independent blue lines in it that, or non-redundant blue lines in it that constrains 3 degrees of freedom. Okay, that's what's called an order of constraint of 3. Okay, a wire flexure, by the way, has an order of constraint of 1 because it just has 1 blue line in it, and it allows 5 degrees of freedom, right? But this has an order of constraint of 3 because there's 3 blue lines in it that are independent, and it allows 3 degrees of freedom. Okay. So let me just repeat what I said. Okay. If on an exam I asked you, is a blade flexure over-constrained in and of itself? Is there a redundant constraint in it? You could, if you want to get picky, you could say, technically, mathematically, yes. It has infinite wire flexures in it. It's very over-constrained according to this argument I gave you. But in practice, it's not useful to consider it over-constrained. So just the short answer is no, it's not over-constrained. It is exactly constrained, but it has an order of constraint of 3. Okay? And you could also get equally picky if I said, is a wire flexure over-constrained? You could say, well, mathematically, technically, other blue lines could fit down its axis because it doesn't have an infinitely thin thing, and so it's technically over-constrained with redundant blue lines in it. But in practice, it's not useful to think of it as over-constrained. It's exactly constrained, and it has a single blue line in it, and it has an order of constraint of 1. And that's going to be true of any element. If I give you a notch flexure or anything else I haven't shown you yet, you will see that they are, in and of themselves, not over-constrained. Technically, yes, they have many redundant constraint lines in them, so they're mathematically over-constrained. And the more redundant constraint lines they have in them, the more they will behave over-constrained in reality. But it's not useful to consider them as over-constrained in analysis. So you just say they have an order of constraint of how many independent non-redundant blue lines were in them. Okay, we'll have a whole lecture on these elements of different geometries, wires, blades, and everything. But for now, you just need to know about wires and blades and this concept of over-constrained and exact constraint. Okay. All right. Okay. So with that, let's do some examples. Okay. Okay. Here's a blade flexure, or here's a flexure system. It's got a single stage here. These wire flexures got 4 wire flexures on the ends of them. They're all attached to a common ground. So I guess the first question could be, is this a parallel or a serial system? Your answer would be, it is a parallel system because it consists of 2 rigid bodies, the stage and the common ground, connected directly together by wire flexures there. So it's a parallel system. Okay. How many degrees of freedom does it have? Well, if I were to draw a bird's eye view here, let's see here, which I don't do in this, unfortunately, but if I were to draw a bird's eye view, you'd see these 3 are on the same plane, and they all intersect. If I drew the blue lines, they all intersect at the same point, which with this one. So this one, if you draw a blue line here, it intersects with this one, and this one. Okay, so that's a little clue. Since, if we draw the blue lines through all 4 of these, they all intersect at the same little point there in the center there where they intersect. Okay, so now the question is, can you visualize, just without using anything I've taught you, can you visualize, knowing that, what degrees of freedom do these things kill? Okay, and which numbers are they? Well, okay, so how many degrees of freedom does it have? Well, how many degrees of freedom does it at least have to have is one of the first questions. You could use Maxwell's equation here to answer this first question. So normally what you do is you take 6, which is, and subtract it from the number of constraints to find out how many degrees of freedom you have. Well, so here there's 4 wires, so 6 minus 4 is 2. Okay, so it has to at least have 2. Now, could it have more than 2 degrees of freedom? Yes. What if one of these wires is redundant? Okay, if it's redundant, then you'd have 3 or 4. So I guess you can use Maxwell's equation in any scenario to find out the least number of degrees of freedom. So this has to have at least 2 degrees of freedom. Okay? Well, okay, we don't know how many it has, so can you actually visualize it? Well, you got to ask yourself, can it translate? No, this wire kills the 1. Okay? Can it translate in this direction? No, this wire kills the 5. Can it translate in this direction? No, the wire kills the 3. Okay? Well, can it rotate around 2? Yes, it can. Can it rotate around 6? Yes, it can. And can it rotate around 4? Well, yes, it's torsion of this one, and it's the instant center of all 3 of these, if they intersect there. So you can imagine you could torsion this one and then do the instant center of those. So 4 works too. So you could visualize that the answer is 2, 6, and 4. 2, 4, and 6 are the 3 degrees of freedom that are allowed. Okay, so that means there are 3 degrees of freedom, but 4 constraints. So the question is, how many redundant constraints are there? Okay, well, remember, if it was exactly constrained, there would be 2 degrees of freedom, because 6 minus 4 is 2. But we found 3, okay, which means one of them is redundant. Okay, so one of them is redundant and didn't do anything, and so we shouldn't have counted it. So now we should have done 6 minus 3 is 3, and that's really how many there are, right? So there's one redundant. And the question is, which constraint is redundant? Well, again, remember that one example where there was no culprit, but let's see if there's a culprit here. Let's see, if I take this one away, does it change anything? Nope, it could still rotate with those 3. This guy could be redundant, okay? If I took this guy away, would it change anything? Nope, it would still rotate with those 3. This guy could be redundant. Whether I added or subtracted, this doesn't do it. Same thing with 3. So any one of these things could be redundant. Only one is, but it could be any one of these 3. What about this one? If I take this one out, would it change anything? The answer is yes. If I took this one out, now you could translate up. So this guy is necessarily redundant, or non-redundant, okay? That one, number 4, is critical. Okay, that's a non-redundant constraint. If we take that out or add it, it will change the degrees of freedom of the system. So be careful. Don't just say, if you know how many constraints are redundant, in this case we know the system is one redundant constraint, don't just say it could be any of the 4. Don't be so glib, check it. It's usually a batch of culprits. In this case, 4 is guaranteed non-redundant, but it could be either 1, 2, or 3. Okay? So then the final question, is the system exactly constrained, or over-constrained, or under-constrained? Well, and that's a trick question, because they should really be 2 separate questions. I should first ask, is the system exactly constrained or over-constrained? Because that's one concept, okay? And the answer is, it is over-constrained. It is not exactly constrained, because it has 1 or more redundant constraints. In this case, it had 1 redundant constraint, okay? All right, well, now the question is, and it should be a different question, but I tried to trick you in this, is the system under-constrained or not under-constrained, okay? Well, the system is not under-constrained, and the reason is because it's a parallel system, right? You can't be under-constrained if you're a parallel system. There's not even an intermediate body that can be under-constrained, and you can't have redundant degrees of freedom because you don't even have more than one stage to have a degree of freedom. So it's not under-constrained. So in this case, the system is over-constrained, and it is not under-constrained. Okay? All right, and here's your solutions on this slide. Okay. Okay, let's look at one other constraint example before our next section. This one is tricky because the wires don't connect the bodies in nice orthogonal ways, so our brains don't like it. But we need to start getting into this if we want a general constraint theory. Okay, so first of all, is this a parallel or serial system? Okay, well, hopefully you say it's a parallel system because it contains two rigid bodies, that one, connected directly together by wires. Okay, so there's only, so that's that. So if I ask you, is this under constraint or not under constraint, right off the bat you say it's not under constraint, it's a parallel system. Okay, very good. Okay, but how many degrees of freedom does it have? How many does it have to at least have? Well, there's 4 wires, so you say 6 minus 4 is 2. It has to have at least 2 degrees of freedom or more if some of these are redundant. Well, I'll give you a hint. None of these are redundant. They're all non-redundant. They're all critical. If you take any of them away, they will add a degree of freedom. Okay? So they're all necessary. None of them are redundant. So I can guarantee you there's 2 degrees of freedom. Okay? So let's draw our old engineer's coordinate system with 3 orthogonal translations, 3 orthogonal rotations, and stick them there. Remember, it's like, well, where would we even stick them? Well, okay, we stuck it on the top. That's kind of arbitrary. But tell me which ones this kills. Which ones remain? Okay, because we know there's got to be 2 of them. Okay, well, let's see here. Can you translate in 3? No, it'll stretch these guys. Forget it. So 3's gone. Okay. Well, can you translate in 5? Well, no. That's like right when it's right there, pulling it that way. Right there, pulling it that way. You can see it would lock it up. It would be like a truss. It couldn't move. Okay. Could it translate in 1? Well, think of it right there. Remember, 1 is going this way. So imagine it moving this way when it's in that configuration. It might trick you because you might say, well, sure it can. It can move in that way. But you're wrong. You're wrong. It actually can't purely translate in that way. It's like a truss. If you have a triangle, you can't move it like that. Okay, and I'll show you in a second why your intuition is deceiving you and thinking maybe it can move that way. Okay, but it can't. It can't do 1. So it can't do 3, 5, and 1. What about the rotations? Can it do 4? Can you rotate in 4? No way. Yeah, you can't twist that. Those things are going to put a nice moment on it, and there's no way you can do it without stretching or compressing these guys. Okay, so no 4. So we're getting down to the wire here. What about 6? Can we rotate in this direction? In other words, think of an axis right there at this point, or right there. Could we rotate around that at this location right there? Nope, not a chance. We can't do it. Okay, so gee, we're down to the wire here. We're supposed to have 2 degrees of freedom, but we've only got one more option. Can we rotate around 2? Well, check it out. 2 would be right there. Right there at the top. And if you see, that is the instant center of all 4 of these guys. You can see they all align and go right up to where that is. So right there is the instant center. Right there is the instant center. So sure, it can do that one. So this one works. Okay, and so that is the instant, and you can see there, the first mode shape, you do a modal analysis, it will nice freely rotate around 2. 2 is dead on, it can rotate there, it's the instant center of all 4 of them. It's the intersection of the plane that the all 4 lie on, the 2 planes that the 2 pairs lie on, right? There it is, that works. But, is Maxwell wrong here? There's 4 constraints, 6 minus 4 is 2, you better darn have 2 degrees of freedom, or you're violating. Now, if that's wrong, Maxwell is absolutely wrong. But no, Maxwell's never wrong. There is another degree of freedom. It's just down here. Okay, this is a rotation that is at the instant center of these guys. Right. So actually go back and see. It's the rotation right there. It's the rotation right there. You see, it's the instant center of all 4 of them. Okay, so it can work there. So, and you can see, here's the next mode shape. It rotates down there, and that's how this stage could move. And so it works. But those are the 2. So Maxwell is correct. 6 minus 4 does equal 2. Those are the 2. The question is, what number is it? Well, it wasn't a number. The whole point of this exercise is to show you that degrees of freedom are not stuck to the old Cartesian coordinate system with orthogonal axes of 3 rotations and 3 translations. That's actually nonsense. Our brain likes to think about degrees of freedom like that because we like orthogonal things and we like things to be nice and clean. But the fact is, degrees of freedom can rotate or be about axes anywhere in 3 space. And in this case, they're 2 skew orthogonal lines. Okay? Okay, so with that, I'm going to take just a quick break and we'll get back to this.